Welcome and hello. This is a video exercise in RIMS. And in this exercise, we are going to be dealing with flood control using inflow predictions. So we're going to see what that looks like in RIMS. Here is my Eclipse. And we're going to start off with a model schematic. So you've probably seen something like this before. We have inflow entering the system, I1. Here's the reservoir, which has a storage, S underscore res1, and then a release through channel C12 to satisfy a downstream demand D2. All right, so pretty simple there. We have a node 1 and a node 2. And then next, I want to talk about getting some actual data. This is going to have some real world data involved. And I'm going to grab some data from CDEC. So if you're from California, you can type CDEC into your Google or anywhere, just water data, CDEC data. This first link here is what we're looking for, California Data Exchange. This is just one of many different sources of water data online. So go ahead and use whatever source you want. But if you want to use CDEC data, that's what I'm going to be using here. And I'm going to be picking on New Bullards Bar Reservoir in Northern California. So if you just need some data, you can also just use this source for dummy data. First, I'm going to come down here to CDEC's station search. All right, and then once that's loaded, I want to specify the sensor type. I want this to be inflow. So I need to make sure that we have inflow data at Bullards Bar. I scroll down here, we are inflow 76. So that's set. I also want to check this checkbox so that it works in the filter. And then the collection type, don't want that. Duration, I'm going to click on daily. I've already checked monthly. There's no monthly. And let's go ahead and see what we get there. So I'll scroll down and then click this search for CDEC stations. Okay, so that loaded up. And now we have all the different stations associated with daily inflow data. So we have Lake Almanar, Bear Lake, Berryessa. Bullards Bar should be towards here it is, New Bullards Bar in Yuba River, Yuba County. So BUL, that's the keyword, that's the sensor ID. So what I'm going to do is just come back up to the CDEC main page and then scroll down to historical data. So here it is. So that loaded up. Now what I want to put in my search terms is the station ID, BUL for Bullards Bar. And then we have a little auto suggest just for confirmation that that's what I want. Yes. The sensor number, this refers to the particular data that I'm looking for. So I want to scroll down to 76, which is inflow. Okay, it looks like we have hourly inflow as well. That's way too discretized because we're actually interested in monthly inflow. So I'm going to just have to convert daily inflow. And then the start date and end date, I'm going to just paste in the data for 7 water years here, 2018 water year through the 2024 water year, and then click on view data. All right, so that loaded up and I have my daily average inflow in CFS from that date range you're seeing here. So if you scroll down to the very bottom, we should have a couple buttons here to export the data in different fashions like copy to clipboard, export to Excel, CSV, print or PDF. All right, so I just clicked the Excel button and then that loaded up right here. Here is the Bullards Bar data. These are the numbers I'm interested in. So I'm going to go ahead and copy these into an Excel file that I have prepared. Then here is the Excel file. I just need to paste this data right here. And boom, here's my inflow data once again. It goes down, 2,500 records or so. That's the number of days in 7 years. And then I also have the date data that I've already pasted in. So the date and the inflow data, that's what we're getting from the download. And then in the next few columns over, I'm parsing out the month, year, and day. Instead of having one row per day, which is the case for the first 7 columns in this spreadsheet, I'm doing 1 month per day over here. So this column 11 is actually just summing up all of the flow in the month of October 2017. Okay, I zoomed in a little bit. And then the next row down is all the sum of the flows in November 2017, December 2017, January 2018, and so on. And then with the number of days in that month, I've made the division. And now this is the actual inflow data that I'm going to be using for my inflow time series data with this model. So we have 7 years of data right here from the internet, which is the average monthly flow. And we're going to be coming back to this data in just a little bit once we're ready to input it into a DSS file. All right, so let me just move that out of the way. All right, next up, we're going to set up our project directory. So this is the structure that I want to use. Here's the main project directory here, and then I'm going to have a folder for DSS and run. And then these 2 files will also create when we set up our project in RIMS. All right, here is my blank project directory. So let's go ahead and start creating some directories. So new, and then folder, ESS, and then the other directory is called run. This is just how me and a few other people set up their files. So, you're welcome to use this method if you want. Within the DSS folder here, I'm going to create a new DSS file, 3 of them, in fact, db.dss. I'm going to delete that .txt extension. And then to copy that, I'm just going to hold down Control and then left click drag F2 to rename sv.dss. And then one more time, I need an init.dss file. And we're going to be adding paths to each of these files a little bit later. All right, back up to the main project directory. Inside this run directory, I want to create a main Russell file. So this is going to be the file that's referenced from our configuration for running the entire model. So I'll say main.wresl. Okay. Alrighty, and I'm actually going to just copy that to save me a couple of clicks in a moment. I'm going to create a system directory as well. So new folder, system. Okay, and then I'll paste in a blank file, boom, and then this is just a blank Russell file. I'll call this inflows, and I have a few more files to add, and objectives. Okay, so I added those files. Next, I'm going to go ahead and open up these files. So let's just open up the main file first. Okay, here's that. Then if I just go Control O or File Open, now I can open up the other Russell files that I have in that system directory. Okay, and I want to order them in a specific way, basically the same order that I am going to include them in the main Russell file. So the inflows file is first, then demands, and then channels. That's good. Reservoirs, constraints, objectives, main. Okay, looking good. One thing I forgot to mention is I also need a folder for lookup inside of run, and I need a couple tables for demand and the reservoir storage. So let me go ahead and add that as well. Back to my directory here, add a lookup folder. I use the terms folder and directory interchangeably. All right, and then 2 files here. It's going to be demand data.table. And then the other one is right here. I just created sres1 data.table. All right, so let's open up those files as well. Boom, and all right. We are good to go. Let's go ahead and start defining our system. Keep in mind, this is the model schematic. So when you think about inflows, demands, the continuity constraints, this is the image that I'm thinking about and sometimes helps me build the model. I'm in the inflows file, and right now I'm just going to be pasting in code and explaining it as I go. This is a state variable, a time series data set with the name iRes1. The type is going to be flow, and then the units are going to be in CFS. In fact, you know what? It probably makes more sense for me to populate the state variables and the initial data, both in the tables and the DSS file, before I start referencing it, because it doesn't actually exist yet. So let's go ahead and do that. I'm going to open up my DSS view. Boom, here it is. And then I'm going to open up that the DSS directory. So here it is. I'm in my project directory, DSS, dv.dss. This is the one that we're not actually going to populate before running the model. Init, okay, we're going to need that. And then also sv. All right, looks good. Let's go ahead and populate init first, since that's quick. Init.dss is selected, and I'm going to come up here to data, manual time series. What I want to do is specify the starting storage of water in the reservoir. So I'm going to paste in this path name. It parsed out the parts when I clicked tab. And then for the start date, I'm going to start it a few months before the actual simulation. So I'm going to say 31 July 2017. And then the start time will be 2400 hours. Units will be in 1,000 acre feet, TAF. And then the type, I'm going to select period average. All right, I'm going to start it at 600,000 acre feet, so 600, and then I'm going to type that in a few times for the 3 months prior to the beginning of the simulation, which will begin right here on October of 2017. All right, so that looks good. I'm going to click save, and we're good to go. If you want to check your data, you can just click the table data, select the path, click the table button, boom, there are the numbers. Okay, I'm going to switch over to the sv.dss file. This is where we're going to specify the inflow data, which we had prepared in Excel by looking up online. I'm going to start by going up to data, manual time series. And then for the path name, I'm just going to paste this in right here. This is for I_res1 flow is part C. That's the parameter. And then now I'm going to start this at the exact same month as the actual simulation is going to start. So that will be 2017, 2400 hours. Units is going to be in CFS, and the type again will also be period average. Okay, let's go ahead and grab that Excel data. So we have this prepared. I'm just going to put on my clipboard, copy it, and then paste it, and then save, and then no. So let's go ahead and take a look at what that plot looks like. Here is the inflow data. We have a 7 water year time horizon and the horizontal axis. And then you can see the flow fluctuates from pretty much 0 up to beyond 6,000 on this 2019 water year. And then it gets pretty high in 2023 as well. So that's the inflow data. One more thing I wanted to do on the inflow data is go to the very bottom of the time series and then just retype this last number a few times. So for the next, say, at least 6 months, we'll go ahead and maybe type in 8 months of data. And I'm just going to repeat this number. The reason we need to do this will be obvious a little bit later, but it's basically because we're going to be looking forward 6 months when doing some sort of inflow prediction. This is just basically so the system doesn't crash or give us any error message. So let's go ahead and click save and OK, and then close that. Okay, let's open up our files once again. We have the inflow defined. I want to go over here to the two tables, which is demand table, and then paste in some numbers. What I'm doing here is just setting a constant downstream demand D2 variable for 550. We haven't defined the D2 variable yet, but we will in just a moment. But I wanted to set it up in a table so this repeats year after year for the specified month, where the first month 1 here represents October. So just be careful about that. And it allows me, the modeler, to modify the actual demand if I wanted to. But right now, I'm just going to keep it constant. Keep in mind, I have the table name right here, demand data. This is the first line. The first two lines in the file you're seeing here are comments. So this is the actual first line that WRIMS sees. So I'm going to click save there, and then come over to the demands file, and then paste in the code svar d2. This is referencing the demand column in that demand data table, which is also the name of the file, demand data.table. While we're populating the tables, let me just go ahead and populate the sres1 data table. I'll talk about this a little bit more when we get to constraints, but basically I'm setting reservoir level penalty values, penalty 1, penalty 2 for both min and max. So I'm just going to save that and we'll come back to that a little bit later. Okay, where were we? Here is the channels.russell file. We only have one channel, which is channel C12. So I'm dividing that up into a C12 min, which is required to satisfy the downstream demand, as well as C12 extra. So min plus extra equals the total C12 flow. The units are in CFS. Okay, the next file over is reservoirs, and I've pasted in my data right here. There are a number of state variables with one decision variable. The one decision variable is the one at the top here that represents the amount of storage or current water in the reservoir. So storage and TAF, those are going to be the kind and the units. Down below here are the penalty values I was talking about. Oops, we don't need this first one. That was something else. But we have 4 constraints. Let me go ahead and make this wider. Okay, hopefully that's not too wide for the video, but it's a lot easier to read, I think. These are the state variables. So what we're doing is reading in the P1 min value, P0 min, P1 max. Oops, I'm sorry, this is P0 max and P1 max right here. So these are the 4 different columns that represent the reservoir volume right here. Now would probably be a pretty good time to show the historic Bullard's bar reservoir data. So let's see here. I have another page, and oh, here it is. Here's the page that shows the current reservoir status for reservoirs in California. Some of the larger ones that are affecting the State Water Project and Central Valley Project. So you can see their size and their current status versus historical. Now, Bullard's bar is this one up here, and it's almost completely full. It has a max capacity of 966,000 acre feet. And if you click on the link, okay, it loads up a lot more information. It's 95% max capacity at this date in the year. It's 110 historical average, which is great for California. And then if you scroll down a little bit, we have the max capacity here at 966,000 acre feet. This blue line right here is the current water year. So we're looking really good. California in general is looking really good here in 2025. This light blue area that you're seeing down here, that's the historical average. And then let me see if I scroll down here, we have the water year across the bottom and then the volume along the vertical axis. Like 1977, that's the red line. That was a very dry year. 1983, that was a particularly wet year. So you see the dry year down here. You see the wet year. That's the lime green color, which looks like this year is pretty much right on that particularly wet year there in 1983. And it looks like the maximum volume was just a few weeks ago. But anyway, I'm looking at this because what I want to do is set that maximum and minimum range. So there's a small penalty if it's exceeded penalty zone 0, and a larger penalty if it's outside of penalty zone 1. So I'm going to be starting this simulation at a reservoir storage of 600,000, which is right about here, the historical average. But then I'm giving it a fairly large range. So for October, this first month in the water year, if I go back to my table here, the first month is right here. That's October. I'm starting it at 600. So that's a range of 500 to 700. These are just numbers I arbitrarily set. So if the storage is less than 500, there's a penalty. And if it's less than 450, there's a larger penalty. Similarly, if the storage or the volume in the reservoir exceeds 700,000 acre feet, there's a penalty, and even a larger penalty if it exceeds 750,000 acre feet in that first month of the water year, which is October. So this is just a way I've sort of created a guide curve to encourage the storage of water in the reservoir to be within a specific range for all 12 months of the year. So that's going to come up in just a moment. Let's go and take a look at our constraints now. Here are the constraints. First, we have continuity at reservoir 1. This is basically at node 1. We have the inflow minus the release, and then that equals the change in storage. I'm going to go ahead and make this a little bit skinnier now. And then we have continuity within that channel C12. So the total flow in channel C12 equals the min plus the extra. That's what we talked about earlier. This is now where we're actually enforcing it. And I don't think there's any reason why we couldn't put this constraint in the channels file. That's kind of up to the discretion of the modeler, but this is just how the RIMS folks have done it in their Springfield example, so I'm just kind of following suit. Next, we have a max in-stream flow demand. So the demand D2, which is set to 550, cannot be exceeded by the actual min, C12 min. So any flow C12 beyond the min, which is beyond the D2, is going to be just classified as extra flow. All right, the next constraint down basically says that the storage in the reservoir cannot exceed the maximum capacity, which is 966. I don't remember if I actually, hold on. Okay, here's the reservoir file. Okay, yeah, so I didn't mention that. Here is the value. It's just a static variable, a state variable of 966, referring to the volume in the reservoir 1 in units of 1,000 acre feet. Okay, so that's that objective, or I should say constraint. All right, down here we have the 4 different constraints associated with trying to keep the storage of water in the reservoir at that specific volume. Remember, we're starting at 600,000. So I have a penalty here. This is enforcing P0 min, and then this is P0 max. So this would be like the 500. This would be like the 700. And then down below here, I have the P1 min. That'd be what the 450, and then the P1 max that referred to the 750, at least for October. The numbers I was just mentioning were for October, and then the other months are in that table right there. These are the numbers I was mentioning. All right. I have made the penalty 10 times the conversion to CFS for P0. And then for P1, I've made it multiplied by 50. So just keep those numbers in mind. I told you that the P1 penalty was going to be higher than the P0 penalty. Well, here are the numbers, 10 and 50. All right, the next file over is the objectives. So here is the objectives. What we're trying to do, the most important objective here is to satisfy the downstream flow requirement by maximizing the minimum in-stream flow, which remember does have a maximum bound of the demand. And then after that, a very small preference is to maximize the storage in the reservoir. All right, and the last file we need to populate is our main Russell file. Nothing too crazy here. We're basically just including all of the files that we talked about in the order that we talked about. All right, so I'm going to go ahead and click save. Let's go over to RIMS now and actually build this model. I'm going to come up to File, New, and then Project. And then with General Project selected, click on Next. I'm going to call the project E12 of flood control. And then I need to reference the path to the project directory. Here's the project directory right here. So I'm just going to copy that path onto my clipboard. and then paste it in. Okay, that looks good. So I'll click finish. That created the .project file. And then the other file I need to create is the launch file. So I'm going to right click on that project, run as, run configurations. All right, I'm going to click on Russell/RIMS2 application and then click on the new configuration button, then resize the window. Okay. And then I'll paste in the name I have on my clipboard. Same thing as the project E2 flood control. It's going to be the only configuration, so there's really no good reason to just not name it the same thing as the project, so I can recognize it over here in the list of configurations. All right, now I need to reference the main Russell file. This is going to be a relative reference starting from the project directory to these particular files. So I know the main Russell file is in my run directory, and it's called main.wresl. Same thing with the DSS files. They're in the DSS directory though. So I'll just go ahead and add these. Okay. And then for part A, I'm just going to be generic and call it project. You can call it whatever project it actually is though. And then state and init. Now for the start date, I'm going to select 2017, October 31st. That's good. And then the end date is 2024 right there. So that's cool. All right, everything looks good on this main tab. I'm going to go over to the configuration tab, click on the checkbox for Russell Plus, and then the last tab I need to visit is the far right one, which is common. Click on the shared radio button, click browse, and then click on the project, which for me is this E12 flood control. Okay, everything looks good there. I'll click apply. That created the launch file. I'm going to click on the close button in this bottom right corner here because I'm not ready to run it, or am I? No, actually I am. I think I'm ready to go. Let's go ahead and see what happens. I second guessed myself there. I'm going to right click on the launch file and then click on run as. Okay, so let's go ahead and see what happens. All right, so that ran. It looks like it. Let's check out to see if we have any results. So I'm going to go over to DSS view, select the dv.dss file, and then click on view, refresh catalog. And here we go. We have some numbers, it looks like. Let's start by looking at the SRES1 path and over that time period. And boom, here is the reservoir storage along the entire 7 years of the simulation. We start at 600, and then we can see that it goes up and down for each year because of the inflows fluctuate. It looks like the year 2021 was pretty low, so we must have had less inflows because we know the demand is constant, but that's pretty interesting. All right, let's go ahead and take a look at the channel data. This is C12, so I'll go ahead and look at that. Looks like our flows are still pretty high. Looks like the max flow right here is 6,000 CFS. And then the minimum flow, it looks like it's satisfying that 500. That's probably the minimum half the time. So yeah, our 550, I'm sorry, 550, 550, 550. And then when it's red, like here's our maximum right here, 4,500, 6,100, 3,700. That's a little bit too high for my comfort. And then we're just satisfying the minimum again in the other half of the year. So let's go ahead and start this exercise and the analysis of modifying the model to satisfy specific flood control conditions. Let's say, for instance, that we cannot release more than 3,000 CFS of flow in any given month. So we would be in violation for these months right here. We're releasing more than 3,000 CFS. So let's go ahead and close this. Let's go back to RIMS, or actually let's go back to our files right here. And I'm going to click on the constraints file, which is here. And I'm going to create a constraint, a soft constraint that says we cannot exceed 3,000 CFS. So I'm going to come down here to the bottom and then paste in this soft constraint here. What we're saying is the flow through channel C12, which is the reservoir release, and the max. If the flow exceeds the max, we are penalizing it by 100 CFS. Or I'm referring to CFS as the measure of penalty because the storage penalty was converted to CFS. So I think that's fair. Okay, we do not have this value yet. We don't have a maximum C12 flow rate defined yet. So let's go ahead and do that. I'm going to click on channels and I'm just going to paste in value 3000 for that C12 max. All right, so let's go ahead and see what happens. I'm going to save that. Before running the simulation, I do want to save the existing data that we've saved here. These paths, or at least the ones I'm most interested in, is the release here, C12, as well as SRES1. So with those highlighted, I'm going to go right click and then rename. And then for part F, instead of state, I'm going to just paste in or type in no max release. So click OK, and then those have been renamed. That way, when I rerun the model, I can reference this original no max release scenario results for both the channel flow, the release from the reservoir, and then also the storage in the reservoir. Okay, back to RIMS. And then I've saved those changes. So let's go right click, run as. So it looks like it ran. You may be wondering, well, go to my constraints. Why did I make this a soft constraint? Off camera, when preparing for this lesson, we had infeasibility when I made it a hard constraint based on all the other parameters. So I just didn't want to waste time. But yeah, when I made it a hard constraint and said absolutely no release greater than 3000, then I got an error message. Okay, so it's probably safer to make a soft constraint and then work your way down to a hard constraint or increase the penalty. Let's go ahead and take a look at our results now. View, refresh catalog. Okay, so now we have two different paths here for the channel in C12. Let's go ahead and see how those compare. Okay, so let's focus in on the first few years here. It looks like 550 is the minimum, so that's good. That's being satisfied. Our original here is in red, and then our modified release is in green. So it looks like there's less release in this month, but our maximum is 6,000, and that's well above 3,000. So yeah, it was obeying the 3,000 threshold a couple times, but honestly, we need to do more work to our model to actually get this to work. Okay, let's go ahead and take a look at the storage now. This is RS Res 1 pass for both the previous simulation with no limit and then the one we just ran. So here is the plot. And yeah, that kind of makes sense. Let's focus in on just the first couple water years. Here's the first simulation, and then here is the one we just ran. It looks like the one we just ran has slightly higher reservoir levels, and that's because we're releasing less water for those specific months. But it looks like, yeah, the top of the reservoir, the max capacity is 966, and that's why we're topping out right here, which is not good. In fact, it may be helpful at this point to zoom out and then add in the P0 and P1 min and max ranges so we can kind of see where our green reservoir line is fluctuating within that range and help us make some better, more intelligent decisions when adding in rules, constraints, and other ways to modify the RIMS program. Okay, so let's see that. I want to put my db.dss file. I can put it anywhere and copy it, but let's just put it here. I'm going to go up to data, manual time series. For the path, I'm going to paste this in. This is going to be P1 min, and then I'll make one for all four, but let's start with this one. The start date I'm going to say is the same as the simulation, 2017, and then 2400 hours. TAF is the units because this is the reservoir storage, and then period average. Okay, so the actual numbers I have prepared in a Excel file, just easy paste in. These are the same numbers we saw in that reservoir table, and then save, and then no. Okay, part F is penalty zones, so I can filter by that if I want. And then here is the actual penalty zones. So let's go ahead and make 3 copies and then paste in the 3 other data sets. So I'm going to go right click, duplicate. First, I'm going to set the next one to P0 min. Okay. Okay. Okay, off camera, I went ahead and added those paths and populated them. So let's go ahead and see what that looks like. All right, very cool. So here are the paths representing the max and min. Yeah, that was penalty 0, and then max and min penalty 1. All right, and that's true for all 7 years. Let's go ahead and add in our reservoir now. I'm going to sort by part B. Okay, here we go. So actually, let's go ahead and look at, yeah, let's look at all the paths. Okay. This looks a little bit busy, but we should see our reservoir right here. The green line is representing the reservoir storage in the 7 years. Make this a little bit larger and then zoom in. Okay, I zoomed in here. We can see and scroll across in time. The reservoir storage, it looks like it's towards the top. And yeah, as I scroll, it for some reason unselects the green line, but you can see it's, yeah, definitely towards the top, not near the bottom penalty range. So there's that. Oh yeah, here's our dry year, which is 2021, which is, fine for flood control. So that's not really what we're concerned ourselves with this particular exercise. But yeah, it looks like it's getting slightly penalized because it's below the blue line, but not the purple line. So that's a 10 penalty, but not a 50 penalty. So it's good to see that that's working. It looks like it is. What would be interesting is if I change the objective function for the storage in reservoir 1, not to be a positive 1, but a negative 1, which means it will try to tend towards the bottom. Like right now, the storage is it's towards the top, and sometimes it's a little bit too high. But when the inflow is pretty much average, we could probably set it to a negative weight, which would influence a little bit more release. So let's go ahead and do that. And then let's see how that affects our plot here. I'm going to go back to our files. I'm going to click on the objectives file. Now, instead of a positive one, I'm just going to change it to a negative one for the storage in the reservoir. Remember, one is a very small constraint or objective function coefficient compared to the satisfying the downstream flow as well as the penalties. Save that and then come back to RIMS. Right click on our launch file, run as. Okay, so that finished up. dv.dss, view, refresh the catalog, and then let's go ahead and open up those paths once again. Okay, I'm going to zoom in on the first couple years here and then highlight our plot. All right, yeah, so definitely a different behavior. The storage in the reservoir is now much lower than it was. And it looks like we're still topping out here at 950 and then 960. That second water year, the 2019 water year, is a problem. Let's go ahead and take a look at the flow rate now. So here is the flow, the release from the reservoir. Remember, we want to not exceed 3000 CFS. And the green line here shows that we have much improvement. So again, let's focus in on 2019. The green line here is no longer 6,000. It looks like it's about as high as 4,300, 4,500 CFS. So that right there definitely helps our model out. Then let's scroll over here. Okay. Again, we're keeping to the maximum 3,000 CFS, except for what looks like just a few months right here in 2023. Now, you may be wondering, what about the inflow? What about the title of this exercise? Let's talk about that right now. The title of the exercise is using inflow predictions to improve flood control. So what I want to do is take a look at the inflow data, state variable, and then here's the plot. Now the inflow exceeds 6,000 right here, and 4,000, 5,000. If we could go ahead and look ahead to the future, which is not too unrealistic because in real life we can measure snow surveys. We have an idea of how much rain is going to come, how much rainfall runoff and snow melt is going to come with different degrees of confidence, of course. But let's go ahead and pretend that we have perfect insight into the next 6 months of reservoir inflow data. So what we're going to do is create a state variable and a decision variable to represent that inflow. The state variable is important. The decision variable is just to print it out into the DSS data. So I'm going to click on inflows, which is right here, come down a couple lines and then paste this code in right here. The comment is track the average inflow for the next 6 months. And then what I'm doing is I'm creating this state variable and it's going to be set to the average of the inflow for the next 6 months. So iRes1 is the inflow in the following time period, which is a month. iRes2, iRes3, I'm adding all that up and then dividing by 6. The next two lines down here is basically just to create a decision variable and then set it to the state variable so that it will write to the DSS file. So without actually changing the model, I'm just going to add this in, save it. It's just going to report what is the average inflow for the next 6 months. So I'll click on RIMS and then let's go ahead and run that. Okay, that is done and it should be in our dv.dss file. So I'll click view, refresh. Here it is. I average 6 months. And then here is the plot for it. So you can see that the average is not 6,000, but it does get up to above 4,000 here. And again, in 2022, because we remember we're looking ahead 6 months. And we're going to use that state variable of this average inflow for the next 6 months to modify our model just by adding a constraint. What I want to do is release more water prior to our main inflow. So remember the peak inflow, for instance, was like early 2019. So we have sort of a warning of that huge inflow a few months earlier. I'm going to go ahead and take a look at this plot here. If we could increase the release for a few months preceding that large inflow, that would really help out with our flood control. So let's take a look at the numbers. So I'm going to click on the table button and then come down here to the last 3 months of 2018 are right here. So we have 550, 668, and 550, and 558 after that. After that, we're topped out, and then here's our violation. So what we want to do is increase the flow or the release from the reservoir for these months, and that would definitely help out with available storage when the big inflows come. I'm going to go ahead and close that. Let's go to our constraints file now. And then at the very bottom, I'm going to paste in a new soft constraint. This is going to be called goal flood control. We're going to set the left-hand side to the release from the reservoir, C12. And what we're going to do here for the condition is if this value is, say, 3000 CFS or greater, then we're going to add a penalty if the release is less than 3000. Now, if the release is less than the right-hand side, which is that value, which got up to almost 4000, so that should be interesting. This may be a little bit too severe. I may want to back off the penalty or even back off this value right here. So let's go ahead and see what that looks like. I'm going to go ahead and save and then run the model, run as. So that ran. I'm going to click on the dv.dss file, view, refresh results. First, take a look at the release from the reservoir. Here is that plot right here. Okay, much improved. Actually, look at that. That's better than I expected. So here is the original release with no constraints, no maximum. And then green, this is the model that we just ran where it shows the constraints. And we're not below 3000, but we're below 6000 and we're even below 4000. So that's pretty great. Now, the bad news is I assume that our reservoir storage may be a little bit too low. Okay, I'm going to add in the P1 min and max values, even though P1 max, yeah. So it looks like our reservoir is hit the bottom. That is no good. And that's because we're releasing too much water. So it happened right here at the very beginning of 2019. And then it looks like it happens again at the beginning of 2023. Let's go ahead and dial back that constraint. So instead of 3000, let's set it to 2000, hit save. And then I'm going to run the model again. That finished up. And then view, refresh. Let's take a look at the channel flows now. Okay. Yeah, but still looks pretty good. We're below 4000 CFS for the release from the reservoir. And then let's take a look at our reservoir storage and boom. Okay. Yeah, still looks pretty bad. You know what I'm going to do? I'm going to make one more modification, and that is to reverse a change that we made at the very beginning. And that is to just set a very small preference to increase the reservoir storage, assuming that all the other constraints and demands are satisfied. We're going to have a slight bias to increase the water in the reservoir. We'll run this model one last time and see, hopefully, if our storage doesn't bottom out. All right, back to WRIMS and then run as, and then our decision variables. Okay. Take a look at the flows. Okay, this definitely demonstrates the trade-off because it looks like our releases from the reservoir now exceed 4000. It's still much better than 6000 and even below 5000, but it's not as good as it used to be because we're simply releasing a little bit more water to satisfy the preference that we just implemented. And our last plot here is going to be reservoir 1, and it shows, okay, it's a slight improvement. So we can see the reservoir levels increase and decrease, and it looks like it still bottoms out right here at 2019, but it doesn't bottom out. We don't lose all the water in 2023. So we're working towards a better solution here. There's a number of different things we could do to improve this. Of course, we could add additional penalties right here. So instead of a P0 and a P1, we could add a P2 penalty. That's even more severe, but further down at a lower storage volume. But anyway, that was all I had prepared for this exercise. What we did was set up a simple model schematic, added real-world inflow from a real reservoir, and then modified some of our objectives and constraints to satisfy a flood control simulation.